Chapter 6, Differential Equations and Mathematical Modeling, 6.1, Antiderivatives and Slope Fields. Your objectives for this lesson are to solve initial value problems, to sketch a slope field, and to evaluate an indefinite integral. Okay, so first off, you can see if we have an equation such as dy dx equals y times ln x, this is called a differential equation because it contains a derivative. So your derivative might not be dy dx, here it is. So, but anything like this with a derivative is a differential equation. That is the definition. Another definition for you, an initial value problem. This says finding a function y of x where we are given its derivative and its value at a particular point. So you've seen before in this class, I could give you the derivative of a function and a point that the original function passes through. Then when I ask you to find the function through that point, this is an initial value problem. We've already seen these. The initial condition would be the point through which the function passes. So that would be the value at the particular point is your initial condition. Okay, when we find all functions y that satisfy the differential equation, we have solved the differential equation. So this is when you have your big f of x plus c. So that's all functions that satisfy that differential equation, because all of these would have your derivative f prime. When we find the particular solution that fulfills the initial condition, we've solved the initial value problem. So when you actually go back and find c, then you solve the initial value problem. Be careful what you are trying to solve for. That will really change what your answer should be. Okay. Example 1. Suppose $100 is invested in an account that pays 5.6% interest compounded continuously. Lucky you, you found an account that pays 5.6% interest. Find a formula for the amount in the account at any time t. So the first thing I'm going to write here, I'm going to define what t is, even though we already have it there. I want to write it again. So let t equal 0 when the initial $100 is deposited into the account. Why? Because you start off with $100. So when the clock starts ticking at t equals 0, you have $100. So our initial value problem we have dy dt equals 0.056 y. Where did this come from? Well, I know that my investment is changing, so that's a derivative, rate of change, with an interest rate of 5.6% written as a decimal. That's 0.056 times y. Okay, so at any instant, the rate of change of y is 5.6% of y. Okay, so the next thing I know here is that y of 0 is 100, which is exactly what I've written up here. At time 0, you have $100. Okay, so let's figure out this problem now. What we are looking for is a function whose derivative is a constant multiple of itself. In other words, you can multiply it by itself and get your answer. So that is a property of exponential functions. And this particular function is what we're going to look at right now. So y of t equals c times e to the 0.056 t. If we took this function and found its derivative, we would have, well, you'd bring this exponent down in front, or at least the derivative of it, sorry. So the derivative of that is 0.056. Then we'd have times c times e to the 0.056 t. Let me write my dy dt here. Okay. And this portion here, you'll see is the exact same thing that I have written above for y of t. So really, this is 0.056 times y of t, okay? Which is what we were looking for up here. You see, you wanted to have the coefficient, 0.056, just like we do, times the original function, y, and we do. So something times the original function. So this is our function, this is the derivative. This is the function that we were looking for. Y of t equals c times e to the 0.056 t. Now, we still need to apply our initial condition to check this. Not to check it, to figure out what c is. So when we apply the initial condition, which was y of 0 is 100, we're going to end up with, so y of 0 equals c times e to the 0.056, and t is 0. So this is 100, and this ends up being e to the 0. Anything to the 0 power is 1, so I have c times 1. So basically c is 100. All right. Let me take this and plug it into my equation that I had up here, because I don't want a c here, I want a number. So move this over. Losing my stuff. And I have y of t equals 100 e to the 0.056 t. Okay, so this is my model that I was looking for. And you all already know from Algebra 2 and other math classes, if I wanted to find how much money I have in my account at a time other than t equals 0, I'm just going to plug that in for the t up here, and whatever I get is how much money I have in my account. So pretty good. Okay, next up, slope fields. These are completely new to you. So slope fields are direction fields. For the first differential equation is a plot of short line segments with slopes f of x comma y for a lattice of points in the plane. And I'm sure that this makes absolutely no sense to you, so let's just go ahead and do one. Example 2, plot the solution curves of the differential equation. And our differential equation right here is y prime equals negative 2xy divided by 1 plus x squared. Okay, to plot this, what you're going to do is, well, let me restrict our points here. So we'll plot this for the points that I'm putting up on here for you. Okay. So that's a fair number of points. Basically what you're going to do, take the coordinates from each of these points, plug in the x value for x, the y value for y. Whatever pops out is your slope, which is y prime. That makes sense since slope and derivative are the same thing. And then you're going to put a little tiny line segment that has that slope at the point. So let's start with, what's this point? -1, 2. So -1, 2. Y prime equals -2 times x is -1, y is 2, over 1 plus -1 squared. So I get on top 4 and on bottom 2. This simplifies to 2. All right, so at my point, I'm going to erase it so that I have some space for my line. I'm going to put a little line segment with a slope of 2. So there it is. You want it to be short. Now let's do at 0, 2. Because that's this point right here. X is 0, y is 2. So we're going to have -2 times 0 times 2 over 1 plus 0 squared. This ends up being 0 over 1, which is 0. So my slope at this point, which I am destroying, is 0. So I'm going to put a little line segment with slope 0. Okay. Next, we have 1, 2. And so we get y prime is -2 times 1 times 2 over 1 plus -1 squared. This gives us a -4 on top and a 2 on bottom, so a -2 is our slope. Okay, so -2 slope looks like that. Okay, so I have my first 3 done here. I'm going to pause. I'm going to keep drawing these and come back with more of these done for you. Okay, and we're back. I've drawn a number more of these lines, more than I originally anticipated to, so you could get a clearer picture of what this will look like. And it kind of, I don't know, it looks like you dropped a bunch of matches on the floor right now. But really what this is good for, and this would be even clearer if I had more of these drawn here, but what you can do is kind of sketch a curve through these. So you can see, or maybe you can't, that it's kind of showing you direction with the tilts of the lines here. So I'm going to try this. My line might not be the best, but I could kind of graph a curve like this. And you might be thinking, well, what about these little pieces on the bottom? Well, I could also graph a curve kind of through those too, like this. And the only difference would be when you antiderive this derivative, this y prime here, whatever your c is what is making the difference between which curve you have. And these little red pieces, they'll go up all the way up here forever, basically. So I could have an infinite number of different blue lines graphed here. The c is very important. So the slope field is good for giving you an idea of what that graph will look like. It's also good when you can't antiderive or you can't do so easily, to at least show you what type of graph you're going to be looking at. So they're useful. They're just a little tricky to picture sometimes. Okay, and that is it actually for part 1 of this video. I will see you again in part 2.